Okay, hello. Welcome back, everybody. Welcome back to the Science, Data, and Analytics track for PyConline AU. I'm excited for the last talk of this this block, and that is Patrick Robotham talking about model selection with Python, an introduction to hyperparameter tuning. Patrick is a principal machine learning engineer at Nimble, and hyperparameter tuning is an important topic in machine learning projects. So yeah, I'm keen to hear what he has to tell us about it. Take it away, Patrick.
Okay, thank you. Good afternoon, everyone. My name's Patrick. I'm a machine learning engineer, and today's talk is about how to choose the right machine learning model. Now, the world of machine learning it's very complicated. Imagine you go to a restaurant and you're asked what to pick to eat, but you're presented with a very, very complicated menu that offers a baffling array of choices. This is kind of the situation we find ourselves in. Now, model selection is the problem of what dish to order, and hyperparameter tuning is the problem of what adjustments to make and what extras to include. Now, a bit about me. I used to work at Eliza, which is an AI consultancy. I was their first data scientist, and I currently work at Nimble as principal machine learning engineer, as Ed mentioned. So why do they need machine learning? Well, this was in the papers recently. Nimble is creating a continuous credit intelligence system based on feeding natural language processing software with customer data in order to explain why a customer was granted or denied a loan. Now, it's actually a very good time for them to do this because there's been a lot of natural language processing research coming out lately. If you ever get the chance, Google GPT-3. You'll just see some really amazing things done with text. So part of my role is just to look after this project. So how do we build a project? And almost all data projects can be broken up into a number of key areas. The purpose of these groups is to generate a bunch of questions to ask the company, and then we progressively answer them. So I can't be completely transparent about what I know about this particular project, but I can continue my restaurant metaphor. So in the business understanding phase, this is all around framing the problem. So in our restaurant, this would be taking the customer's order. Data understanding is about understanding our ingredients. Data prep is about preparing the ingredients, chopping the vegetables, etc. And modeling, which is really what this focus is, which is what the focus of this talk is about, is actually cooking the meal. In less metaphorical language, we want to predict a model. We want to create a predictive model. And in the case of Nimble, it's about creating a predictive model that can explain why a customer was approved or denied the loan. Evaluation would be tasting our meal, and deployment would be serving the meal to a customer. So modeling is what we're going to focus on. So here's a sort of more granular understanding of how we do modeling. So assuming we have good data to train on, there are sort of 5 stages in modeling. Number 1, we need to select our modeling technique. And for any problem like this, there are often a bunch of possible mathematical models and algorithms that we can apply. And part of our job is just to decide on what the best algorithm is to use. We then generate a test design. Machine learning is almost never correct 100% of the time because the real world is messy. And, if we could get it 100% right all the time, we'd just be doing regular programming. So we want to work out a way of testing whether we got our modeling approximately right. By the way, it's very common in machine learning to have a training set and a validation set, and to split our data up, and that'll come in handy later. Next, we need to set up the model. And unfortunately, most machine learning algorithms have settings that the algorithm cannot really learn from the data. So for example, you may want to trade off model complexity against how well you fit the training data. If you have a really complicated model with lots of parameters, maybe more parameters than data points, then you can fit the data extremely well because you can just memorize it. But this will generalize to new situations quite poorly. So some settings are not learned from data, and these settings are called hyperparameters. And notice I said are not and not cannot. Whether or not a parameter can be learned from data is a property of the algorithm. Finally, we need to fit our model to our data and then assess how well the model has performed. So our first task is model selection. To repeat my analogy, the world of machine learning is a restaurant with a very complicated menu. And there's lots of possible dishes you might order and lots of alterations that you can request. So model selection is about working out what we want to eat. So what's on the menu? Well, the problem we face is there's too many models. If you Google machine learning, you'll come across terms like these, terms like deep learning, kernel, Monte Carlo Markov chain, regularization, gradients, etc., etc. And personally, I find this can have quite an intimidating effect. And the good news is you don't need to know what these terms mean in order to choose the right model. Well, how do we choose the right model? Well, what we need is a very simple selection process. Let's really cut down the complexity. Unfortunately, when I Googled this, what I found with this sort of semi-complicated flowchart, and I actually think this flowchart has the right idea, but we can get even simpler. What this flowchart is good for is getting us into one of these colored circles. Each circle kind of represents a kind of machine learning problem with a definite input and output. Now, here's the same flowchart without all the models. By the way, these models in the previous slide, they're mostly obsolete. New models have been discovered since this flowchart was published. The restaurant of machine learning changes its menu every season. But the important thing is defining the problem. Let's work out what sorts of inputs the model takes and what sorts of outputs it needs to produce. For example, classification takes in numeric data and produces an integer. So even simpler, look at the inputs and outputs. Now, maybe that's a bit too simple. But when we're looking at the menu of machine learning models, we can drastically cut down our choices by applying the principles on this slide. So number one, as I've stated several times, just check whether the inputs and outputs are compatible with your training data. And this is one of the reasons why it's important to understand your training data so well. Number two is check whether the machine learning model is supported by hardware that you have access to. So for example, if you have a Mac, running deep learning frameworks like Torch require graphics cards that are written by NVIDIA. But unfortunately, Mac has a Radeon graphics card, so deep learning will be kind of slow on your Mac. So it's very important to understand your deployment process and where your model will eventually live. Number three, and this is just check whether your machine learning model is fast enough. Some machine learning models are very accurate, but also very slow. This is what happened to the winner of the Netflix prize, for instance. Netflix had a competition that offered $1 million prize to the model that could produce the best recommendations for movies to watch. But the winning model was never actually used because it was too slow. Netflix customers want their recommendations now, not in 20 seconds. When you evaluate models, you need to include speed in your criteria. And number four, check whether the model is explainable enough. Now, this depends on relevant law, who will be using the model and why, but in some scenarios, people have a right to an explanation. So you need to understand the problem and the business context. So after we've cut down our choices, there are sort of three scenarios we might face. We might have 0 options available off the shelf. And in this case, we're in the realm of research and development. And this is good news because you can get a tax break, but it's bad news because it's unknown at this stage whether the problem we're trying to solve is actually viable. Now, 2 model development frameworks I like for doing R&D are neural networks and Bayesian statistics, and this is because they can handle a very wide variety of data types. But this is not what this talk is about. Now, we might have 1 model available, in which case we can just use it, or we can make our own if we're not happy with the model. And finally, we might have a number of models available, in which case I assert that if the models all have the same inputs and outputs, the problem of which model to use is a hyperparameter in a meta model. So we can turn our n models into one. So what are hyperparameters and what is hyperparameter tuning? Well, if model selection is about working out what dish to order, then hyperparameter tuning is working out all the extras and adjustments. So I do model selection when I order the green curry, and I do hyperparameter tuning when I order it without rice and for it to be extra spicy. If model selection is about working out what song to play, then hyperparameter tuning is about setting the knobs in our mixer to their best levels. We want to kind of twiddle these knobs just right so that we can get the best model possible. So that's hyperparameter tuning. And to be more specific, a hyperparameter is a setting for a machine learning algorithm that cannot be learned by the algorithm itself. So for example, this regularization lambda hyperparameter here trades off model complexity against goodness of fit. And kind of the problem we're facing is that this thing has 22 hyperparameters, and I only have 25 minutes to give this talk. And again, the good news is we don't really need to know what all these hyperparameters mean in detail in order to select the right values for them. Though you should learn a little bit about the hyperparameters for your model. But this is a really intimidating part of machine learning. You know, I do a tutorial, I learn how to pre-process my data, I learn how to fit a model, I maybe even learn how to deploy with things like Docker. But when I really get to the modeling part, I encounter stuff like this documentation right here. And often I'll be linked to some sort of academic paper that explains what the setting means in complicated mathematics rather than be told in plain English. And it kind of, well, I kind of like it because it keeps my salary high because there's not that many machine learning engineers available to compete with me. But in general, this is kind of bad. We don't want to read papers just to work out whether this should be a 3 or a 2, right? So this is me trying to initialize my XGBoost regressor, trying to decide what hyperparameters to use. Now, to make this even more concrete, this is PyCon after all, so let's do some Python. This is some Python code that actually creates an XGBoost regressor model. I've colored the hyperparameters in yellow. Now, as you can see, most of the actual modeling code is selecting what hyperparameters to use. So to start with, we import XGBoost. We then create our regressor object. Our objective is to minimize the mean squared error, which is the difference between our predicted value and the actual value squared. Our evaluation metric is mean absolute error. I use this because Nassim Taleb told me to. And the hyperparameters are all in yellow, things like cold sample, by tree, and learning rate, and n estimators, and so forth. And I'm not going to explain what they mean because you don't need to know. But how do we pick the right values for our hyperparameters? So one idea, which is pretty popular, is to plagiarize. You know, just look at published papers and Kaggle competitions and use whatever hyperparameters they use. Now, the downside of this approach is that the hyperparameter settings may not be suitable for your particular use case. You know, they worked out the hyperparameters to solve their problem, which may not be the same as your problem. It's the same problem with like just borrowing model weights. And another thing we can do, and I actually had a colleague who was very good at this. Another thing we can do is experiment. Try different settings and keep track of how well they perform. After you tinker enough, you might stumble upon something that works. And the downside to this approach is that it's very time consuming. You have to write a lot of code and do a lot of copying and pasting. Or finally, we could use AutoML services. And these are programs that will choose the right hyperparameters for us. Now, I assert, and the providers of these services agree with me, that the problem of choosing what parameters to use in a machine learning algorithm is itself a machine learning problem. I'll say that again. The problem of choosing what parameters to use in a machine learning algorithm is itself a machine learning problem. Yo, dog, I heard you like neural nets, so we put a neural net in your neural net so you can learn while you learn. So what does this actually mean? How can a program choose the right settings for our model? Well, a problem well stated is HalfSoul, so let's actually state our problem precisely. So there's going to be a bit of maths here because mathematics is the language of machine learning. So my problem is to, so again, let's take my nimble problem. I want to work out whether a customer can afford to pay back their loan based on their loan application data. So X would be the input, Y is hand annotated outputs or labels, and H is the model in question. So what machine learning algorithms do is that they minimize some sort of loss function, and they find the parameters for our model, and that's fine. So really, given our data and our labels and our loss function and our hyperparameters, machine learning algorithms will find the best set of rules to make the best prediction. And what AutoML services do is, given our data and our labels and our loss function, or our evaluation function, find the best set of rules to make the best prediction, as well as the best set of hyperparameters. So we go from simply searching over our parameter space to searching over both our parameter space and our hyperparameter space. So that's our problem defined mathematically, but how do we solve it? And one candidate is the random search algorithm. Throw everything at the wall and see what sticks. To elaborate on this, start by splitting our data into a training set, which is used to train a model, and then a validation set, which is used to test the model. Then we generate a random set of hyperparameters. We fit our model to the training set. We evaluate based on the fitted model, based on the evaluation set, the validation set. We then record the results, and we repeat forever, or until we get bored, or until a pre-specified number of experiments has ended. I guess this pre-specified number would be a hyperparameter. And finally, we select those hyperparameters that did the best on the validation set. Now, this works because it's simply an automated version of tinkering. We try different settings over and over and over and over again. And a computer, this algorithm is just really parallelizable. A computer can do this really fast. And you can even have different computers trying out different hyperparameter settings. So we can go from trying out a new setting every day to trying a new setting every second. And this algorithm has actually been implemented in scikit-learn, which is a machine learning library for Python. And this is some code that will find the best hyperparameters for the XGBoost regressor. We start by importing libraries. We then load our data. We then define not the hyperparameters, but the range of possible values that we want the random search algorithm to consider. We then set up random search and point it at our training data. And then the output will be the best set of hyperparameters discovered within the range that we specified. And so you find the output is something like this. You have a model, the hyperparameter settings, and various measures of how each model performed. And you can sort this table by any particular metric. And all you have to do is pick the top row in the table. So we've chosen our meal. We've had our dinner. And now for the after dinner conversation. Oh, what do we learn? Well, we learned what a hyperparameter is. We learned that there are services and algorithms that will find the best hyperparameters for us. And we've learned that the key to successful machine learning projects is palming the work off onto someone else, ideally a computer. But I wanted to contextualize this learning by asking a sort of philosophical question, which is, how does a data scientist really earn their salary? And I would say that a data scientist's true value, it's not in selecting the right hyperparameters or even the right model, but really in framing the problem, working out what problem it is that we're trying to solve in detail, and what data that we can bring to bear to inform that problem, and also how we can evaluate the quality of any solution. And this is the true art of machine learning. And the rest of the stuff can be automated. Even things like pre-processing and learning structure. There are algorithms out there that can automate some of that. So if you want to make good machine learning models, start by framing the problem. Define very precisely what are the inputs and what are the outputs. And then look at how you can add more information and get new sources of data for your problem. And only after all of that do you pick your model. And what I typically do is I use an AutoML service. I make a coffee, chat with my colleagues, come back in half an hour, and my model has been selected and my hyperparameters have been set. Thank you very much. I'm aware I've gone a little bit early. Are there any questions, Ned?
Hey, yes, thank you for that, Patrick. That was a great talk. We do have time quickly for one or two questions. So we have a question from Ben, and it's saying, isn't using ML methods to find hyperparameters slow? Doesn't that make the whole process very slow because we need to train the algorithm with the specific hyperparameters, all the way through to the end? Or are there ways to shortcut around obviously bad hyperparameters early?
Yeah, that's a really good question. So I guess there's kind of two responses. Number one, we can use better algorithms than random search. So there are so-called Bayesian hyperparameter tuning approaches that sort of learn which areas of hyperparameter space to stay away from. I think the other thing I would say, though, is that it can be slow, but it's also intensely parallelizable. So if you can get familiar with concurrency, then you can kind of go wide and just use more computers to speed things up. But it's a really great question.
Yeah, cool. Okay, one more question I think we can squeeze in. When you're jumping into a project, do you have some heuristics for like when to do the tinkering versus when to do the AutoML? Like at some point you sort of have to start with something, right? And when do you sort of make the switch?
Yeah, it's a really good question. And I might go back a few slides just to kind of answer it more. So I guess this is so what I would typically do is I almost always start in this area of stealing someone else's code and adapting it, because there's so many just fantastic tutorials out there. And I guess I just have a very strong rule not to. It's one thing. So what I typically do is I tinker when I'm doing feature engineering and trying to add new data sources. And I might do a little bit of tinkering if I suspect there's some problems with overfitting or such like, just to see if any improvement at all on my default set of hyperparameters is possible. But once I've found that any improvement is possible, then I move to something like randomized search. Any other questions?
I think we might just have hit the end of our time slot.
Oh, darn.
So yeah, but we do have a lot of people enthusiastically talking away about this stuff over on the Venulous channel. So if you've got time, jump over there, and
Yeah, absolutely.
hopefully we can continue the conversation on. So that's the end of this block that we're on now. We're going to have around an hour break before we come back for our third and final block of the science data and analytics stream. And there is, of course, more PyConAU goodness coming up over the rest of the weekend. So I hope you stick around for the rest of the day and also hopefully for some of the rest of the weekend. And I'll, yes, catch you in the Venulous chat.